Time feels obvious. It passes. It carries moments forward. It places a distance between memory and now. You don't need to prove it exists. You feel it every second. The slow movement of a clock, the change in light outside a window, the sense that this moment is replacing the last. Time feels so real that questioning it almost feels unnecessary. And yet, when physics looks closely, time begins to behave strangely. Tonight, we begin with a simple, unsettling idea. What if time is not what we think it is at all? What if it isn't a fundamental part of reality, but something that emerges only under certain conditions? What if the universe, at its deepest level, does not experience time the way we do, perhaps not even at all? This documentary is a slow journey through that question. Not a rush toward answers, but a careful exploration of why some of the most serious scientists in the world now suspect that time, as we experience it, may be more like a sedge than a structure. Something we feel deeply yet struggle to find when we examine the foundations of reality. If you enjoy calm, thoughtful explorations like this, long journeys through deep ideas designed for focus, rest, or sleep, you're gently invited to like and subscribe. It helps the channel continue making quiet science for curious minds. We'll move slowly. There is no need to hurry when discussing time. At the surface level, time seems universal. A second feels the same everywhere. A day is a day. A year is a year. But this sense of universality is an illusion created by human scale. The deeper physics looks, the less stable time becomes. It stretches, it slows, it splits. And in some equations, it disappears entirely. To understand why scientists even question time's existence, we need to step away from clocks and calendars and look at what time actually does in physics. In everyday life, time orders events. One thing happens, then another. Causes come before effects. You wake up before you sleep. Fire burns paper after the match is struck. This ordering feels so natural that it's hard to imagine reality without it. But physics doesn't begin with feelings, it begins with equations. And equations do not always agree with our intuitions. In classical physics, time plays a simple role. It is a background parameter, something that ticks forward uniformly while objects move through space. Isaac Newton described time as absolute, flowing the same everywhere, independent of anything else. For centuries, this idea worked remarkably well. It explained falling apples, planetary motion, tides, and machines. Time was reliable, invisible but dependable. Then in the early 20th century, that certainty cracked. Albert Einstein showed that time is not absolute. It is intertwined with space, forming a single structure called space-time. According to relativity, time does not pass at the same rate everywhere. It slows down near massive objects. It slows down for objects moving very fast. Two observers can experience different amounts of time between the same events, and both be correct. This was not a philosophical suggestion, it was a measurable fact. Atomic clocks flown on airplanes tick differently than those left on the ground. GPS satellites must correct for time dilation or they would quickly become useless. Time, it turns out, is flexible, but flexibility alone does not mean unreality. A rubber band is flexible, yet very real. The deeper problem comes later, when physicists try to combine relativity with quantum mechanics, the theory that governs particles, fields, and the smallest scales of existence. This is where time starts to fade. In quantum mechanics, time plays a different role than space. Space is something particles can be in superpositions of. Time is something that simply flows in the background. But when physicists attempt to build a theory of quantum gravity, a framework that describes space-time itself at the smallest scales, time often vanishes from the equations altogether. One of the most famous equations in this effort, the Wheeler-DeWitt equation, contains no time variable. None. The universe it describes does not evolve in time. It simply exists as a complete mathematical object. This result is so unsettling that it has been called the problem of time in physics. If the most fundamental equation describing the universe has no time, then where does time come from? And why do we experience it so vividly? This is not an abstract puzzle. It cuts to the core of reality. Because if time is not fundamental, then the universe at its deepest level may be timeless. No past, no future, no flow, just structure. And yet here you are, listening now, aware that this moment is different from the one before it. So something must bridge that gap. One way to approach this is to ask a quieter question. What do we actually mean when we say time is passing? Is time itself moving, or are events simply arranged in a certain way, giving us the impression of motion? Consider a film reel. All the frames exist at once, laid out in order. Nothing inside the film is moving, yet when projected, motion appears. The sense of flow comes from how the frames are experienced, not from the film itself. Some physicists suspect time may be similar. The universe may be a static structure, a vast configuration of states, while our consciousness moves through correlations within it, creating the feeling of passage. This idea is sometimes called the block universe. In this view, the past, present, and future all exist equally. There is no objective now. What we call the present is simply the slice of space-time we happen to be experiencing. If that sounds unsettling, it's because it challenges a deeply human assumption that the present moment is special. But physics has already taken away many ideas that once felt obvious. Earth is not the center of the universe. The sun is one star among billions. Our galaxy is one among trillions. Time may be another such assumption, intuitively powerful yet not fundamental. Still, even in a block universe, something remains unexplained. Why do we remember the past but not the future? Why does entropy increase? Why does disorder tend to grow? Why do causes seem to precede effects? This is where the arrow of time enters the story. The arrow of time refers to the fact that many processes in the universe are asymmetric. A glass shatters but never spontaneously reassembles. Heat flows from hot to cold, not the other way around. These processes give time a direction, even if the underlying laws of physics are mostly time-symmetric. At the microscopic level, many physical laws do not care which way time points. They work just as well forward as backward. Yet at the macroscopic level, the universe clearly prefers one direction. This suggests that the flow of time may not be built into the laws of physics themselves, but into the conditions of the universe, especially its initial conditions. In other words, time may emerge from complexity, not dictate it. Some physicists argue that time arises from change, others suggest it arises from entanglement. Some propose that time is a statistical phenomenon, a byproduct of how information is distributed, and a few take the radical step of saying that time is not real at all, only correlations are. What unites these ideas is a shared discomfort with treating time as a fundamental ingredient of reality. Space can be measured, energy can be quantified, fields can be described. Time, however, resists being pinned down. The more precisely we define it, the more it slips away. This is not because scientists are careless. It is because time behaves differently depending on how closely you look. At human scales, time is reliable. At cosmic scales, it stretches. Near black holes, it slows almost to a halt. At the quantum level, it may not exist in the way we imagine. And at the beginning of the universe, time itself may have emerged from something deeper. If time had a beginning, then it is not eternal. And if it is not eternal, then it is not fundamental in the way we often assume. This leads to one of the strangest ideas in modern cosmology, that asking what happened before the Big Bang may be meaningless, because time itself may have started there. Without time, there is no before. Yet even this idea is being questioned. Some models suggest that time may emerge differently in different regions of the universe. Others suggest cyclic universes, where time resets or loops, and some suggest that time is not a dimension like space at all, but a bookkeeping tool we use to describe change. Throughout this documentary, we will explore these possibilities carefully. We will look at how time behaves in relativity, how it disappears in quantum gravity, how entropy gives it direction, how consciousness experiences it, and why the universe seems to remember the past but not the future. But for now, it is enough to sit with the question itself. Time feels real because it organizes our lives. It gives meaning to memory and anticipation. It allows stories to exist. Without time, there is no narrative, only structure. And yet, Physics suggests that the universe may not tell stories in the way we do. It may simply be. If that is true, then time is not a river carrying us forward. It is a perspective, a way of reading the universe from inside. As we continue, we'll move deeper into this idea. We'll examine how time stretches near gravity, how it fractures in quantum mechanics, and how some theories rebuild reality without it. For now, let this thought settle gently. The universe may not be rushing anywhere. It may already contain every moment that ever was or will be. And what you feel as now may be something very rare indeed. When time slows down. If time might not be fundamental, then the first step toward understanding that idea is to see how easily time can be changed. Not imagined differently, not philosophically reframed. Physically changed, slowed, stretched, unevenly distributed across the universe. This is where relativity quietly reshaped reality. Before Einstein, time was treated as a universal metronome. It ticked the same for everyone, everywhere. You could argue about distance, speed, or direction, but time itself was assumed to be absolute. 1 second for you was 1 second for the universe. Relativity removed that assumption. According to Einstein's theory, time depends on motion and gravity. The faster you move through space, the slower you move through time. The stronger the gravitational field you're in, the slower time passes for you compared to someone farther away. This is not metaphor. It is measurement. Two identical clocks, synchronized perfectly, will disagree if one is moved faster or placed deeper in a gravitational field. The clock near the massive object will tick more slowly. The clock in motion will fall behind. Neither clock is broken. Time itself has diverged. This immediately raises a quiet but profound question. If time can pass at different rates, which one is the real time? The answer, according to relativity, is uncomfortable. There is no single universal time. There is only local time, time measured along each observer's path through space-time. Every observer carries their own version of time shaped by their motion and environment. This means the universe does not share a single now. Events that appear simultaneous to one observer may not be simultaneous to another. The idea of a global present moment dissolves. Instead of a universal timeline, space-time becomes a woven fabric of many timelines, each valid within its own frame. At human speeds and weak gravity, these differences are tiny. They fade into the background of daily life, but they are not zero. And at extreme conditions, they dominate reality. Near a black hole, time slows dramatically. To a distant observer, an object falling towards the event horizon appears to freeze, its clock ticking slower and slower. From the falling object's own perspective, nothing unusual happens at the horizon. Its own time continues normally. Both perspectives are correct. This alone tells us something important. Time is not a shared substance flowing everywhere at once. It is relational. The closer you look, the more time behaves like space. It stretches, it contracts, it curves, and in relativity, space and time are not separate at all. They are aspects of the same structure. This unification is elegant, but it carries a cost. Once time becomes just another coordinate, something strange happens to causality. The order of events can change depending on perspective. In some frames, event A happens before event B, in others, B happens before A. As long as the events are not causally connected, physics allows this. So the universe does not insist on a single ordering of all events. This is unsettling because our experience depends on ordering. Memory requires sequence. Language requires before and after. Identity itself seems to require continuity through time. Yet physics shows that sequence is not absolute. This is where the block universe idea gains strength. If space-time is a four-dimensional structure, then every event, past, present, and future exists as part of that structure. There is no moving spotlight of now sweeping forward. There is only the structure itself, complete and static. In this view, time does not flow. We move through space-time the way a reader moves through a book. The story exists all at once. The sense of progression comes from how it is experienced. Relativity does not force this interpretation, but it allows it naturally. And once allowed, it solves many puzzles. It explains why there is no universal present. It explains why different observers disagree about simultaneity. It explains how time can slow down without contradiction. But it introduces a deeper mystery. If the universe is a block, and all moments exist equally, why do we experience only one moment at a time? Why does consciousness feel like it is moving? Physics does not answer that directly, but it hints that time as we feel it may not be something the universe is doing. It may be something we are doing. To see why, it helps to look at another strange feature of relativity, the fact that time can be traded for space. In space-time diagrams, time and space are coordinates. Rotate your frame of reference, and what counts as time for one observer becomes a mixture of time and space for another. This is not just mathematical convenience, it reflects physical reality. What this suggests is that time is not a separate substance flowing independently. It is part of the geometry of the universe. And geometry does not flow. Mountains do not move forward. Distances do not pass. Shapes simply exist. If time is geometry, then flow may be a perspective effect, not a property of the universe. This idea becomes even more striking when we consider how clocks actually work. A clock does not measure time directly. It measures change, a pendulum swings, a crystal vibrates, an atom oscillates. We define time by counting changes in physical systems. Without change, time has no operational meaning. This leads some physicists to argue that time is not fundamental but derivative. It emerges from the relationships between changing systems. If nothing changed, time would be undefined. In relativity, this becomes literal. Proper time, the time measured by a clock, is defined along a path through space-time. It is not something external. It is something accumulated through motion. Time is something you experience by existing. This raises a subtle but important shift in thinking. Instead of time being a river that carries objects forward, objects carry their own time with them. Each path through space-time has its own temporal length, and because paths differ, times differ. At this point, time already looks less like a universal background and more like a personal measurement. It depends on where you go, how fast you move, and what gravity you encounter. But even this is not the end of the story, because relativity still assumes time exists as part of space-time. It bends, it stretches, but it is still there. The real trouble begins when we ask what space-time itself is made of. General relativity describes space-time as smooth and continuous. Quantum mechanics, on the other hand, describes reality as discrete and probabilistic at the smallest scales. When physicists try to combine these ideas, time begins to evaporate. In some approaches to quantum gravity, space-time is not fundamental. It emerges from more basic structures, networks of relationships, information, or quantum states. And in many of these formulations, there is no time parameter at the deepest level. Instead, there are correlations. One part of the system changes relative to another. One configuration relates to another. But there is no external clock ticking forward. This suggests a radical possibility. Time emerges only when we look at the universe from the inside, as part of a system observing itself. From the outside, if such a perspective even makes sense, the universe may simply be a static pattern of relations. Relativity opens the door to this idea by removing absolute time. Quantum gravity pushes it further by questioning time's existence altogether. And between those two theories, the ones that describe the very large and the very small, time finds itself in an uncomfortable position. It works perfectly well where we live. It becomes flexible where gravity and speed matter, and it may vanish entirely where space-time itself breaks down. This does not mean time is an illusion in the everyday sense. It means time may be emergent, like temperature or pressure. Real, measurable, powerful, but not fundamental. Temperature feels basic, yet it emerges from the motion of particles. Pressure feels solid, yet it emerges from countless microscopic collisions. In the same way, time may emerge from deeper, timeless processes. If that is true, then the flow of time is not something the universe does. It is something that happens when systems like us exist within it. As we move forward, we will look at the arrow of time, the reason time seems to have a direction. We will explore entropy, disorder, and why the past feels fixed while the future feels open. But for now, it is enough to notice this. Time can slow down. It can stretch. It can disagree with itself. And anything that can do all of that begins to look less like a fundamental law and more like a consequence of deeper structure. The universe may not be moving through time. It may simply be arranged in a way that makes time appear. The arrow that points forward. Even if time can slow, stretch, and disagree with itself, there is still one feature of time that feels unshakable: direction. Time moves forward. We remember yesterday, not tomorrow. Causes come before effects. Eggs break, but they do not unbreak. No matter how flexible time becomes in physics, it seems to have an arrow. This arrow of time is not defined by clocks, it is defined by experience. You can watch a video of a shattered glass played backward and immediately know something is wrong. The laws of physics at the microscopic level do not forbid the reversed motion, yet your intuition rejects it. This tells us something important. The arrow of time is not obvious in the equations, it is obvious in the outcomes. The question is why? In most fundamental physical laws, time is symmetric. They work just as well if time runs backward. The equations of motion in classical mechanics, electromagnetism, and even quantum mechanics mostly do not prefer a direction. They describe relationships, not flows, and yet the universe clearly prefers one direction. This mismatch between time-symmetric laws and time-asymmetric experience is one of the deepest puzzles in science. It suggests that the arrow of time does not come from the laws themselves, but from the conditions under which those laws operate. The key concept here is entropy. Entropy is often described as a measure of disorder, but that description is incomplete. A more precise way to think about entropy is as a measure of how many microscopic arrangements correspond to the same macroscopic state. High entropy states are more probable because there are more ways for them to exist. A neat stack of papers can be arranged in very few ways. A scattered pile can be arranged in countless ways. If you shake the system, it is far more likely to end up scattered than neatly stacked. This statistical tendency gives rise to the arrow of time. The second law of thermodynamics states that in an isolated system, entropy tends to increase. Not because it must, but because it almost always will. High entropy states are overwhelmingly more likely than low entropy ones. This explains why processes feel irreversible. Shattering a glass increases entropy. Reassembling it would require an extraordinarily specific rearrangement of particles, possible in principle, but so unlikely that it effectively never happens. Time's arrow, then, is tied to probability. But this explanation raises another question. If the laws of physics allow entropy to increase or decrease, why did the universe start in a low entropy state at all? Why was the early universe so ordered? This question reaches back to the beginning of time itself. Observations suggest that the universe began in a remarkably low entropy condition. Matter and energy were distributed smoothly with very little gravitational clumping. This initial order is what allows entropy to increase over time as structures form, stars burn, and systems evolve. But why was the beginning special? Physics does not yet have a complete answer. Some theories propose that the low entropy beginning is a fundamental boundary condition. Others suggest that our universe is one region within a much larger multiverse, and that low entropy beginnings are rare but necessary for observers like us to exist. There are also ideas suggesting that entropy increases away from a central low entropy point in both temporal directions. In such models, what we call the past and the future are simply opposite directions of increasing entropy, and our sense of forward is tied to the direction in which entropy increases for us. If that were true, time would not be fundamentally directed. Direction would be local, emergent, and perspective dependent. This possibility challenges the idea that the universe has a single arrow of time. It suggests instead that arrows emerge where conditions allow them to. From this perspective, the flow of time is not a global feature of the universe. It is a feature of thermodynamic systems that start in special states. We live inside one of those systems, and our memories, biology, and consciousness are all aligned with entropy increase. Memory itself depends on entropy. To remember something, you must create a physical record. Creating records increases entropy. This means that memory can only point toward lower entropy states. You remember the past because the past is where entropy was lower. The future has higher entropy, and therefore fewer stable records. This is why you do not remember it. This connection between memory and entropy suggests something profound. The psychological arrow of time, the feeling that time flows from past to future, may be inseparable from the thermodynamic arrow. In other words, time feels like it flows forward because that is the direction in which information accumulates. This makes the flow of time feel less like a fundamental motion and more like an information gradient. Consider a simple example. Imagine a room where ink diffuses in water. At first, the ink is concentrated. Over time, it spreads out. If you see the ink spreading, you can tell which way time is moving. But if you only see a uniform mixture, you cannot tell whether time is moving forward or backward. The arrow exists only where there is a gradient. In the universe, entropy gradients give time its direction. Where gradients exist, time feels like it flows. Where everything is already maximally disordered, time loses its meaning. This leads to a strange but elegant conclusion. Time does not pass everywhere equally. It passes where change is possible. In regions of the universe near thermodynamic equilibrium, time becomes difficult to define. In the far future, when stars have burned out and matter has spread thinly, entropy may be so high that little changes. In such a universe, time may still exist mathematically, but experientially it would be almost empty. Some physicists suggest that time itself could fade in such conditions. This does not mean the universe ends. It means the universe becomes static in every meaningful way. If time is tied to entropy gradients, then time had a beginning not because the universe started ticking, but because the universe started far from equilibrium. And time may have an end not because clocks stop, but because nothing meaningful changes. This reframes the question of time's reality. Time is not a river flowing independently. It is a measure of how far systems are from equilibrium. This also explains why time feels so deeply real to us. We are far from equilibrium systems. Our bodies, brains, and environments are constantly processing energy, creating entropy, and storing information. We exist inside steep entropy gradients. As long as those gradients exist, time will feel vivid. But this view also suggests that time's direction is not written into the universe itself. It emerges from the universe's state. The arrow of time, then, is not something that pushes events forward. It is something that emerges because the universe began in a special way. And this leads to one of the most unsettling ideas of all. If the arrow of time depends on initial conditions, then time, as we experience it, is contingent. It could have been different. It might be different elsewhere. It may not exist at all in some regions or phases of reality. Time may be local. As we continue, we will look at what happens to time in quantum mechanics, where even the idea of a definite sequence of events becomes uncertain. We will see how entanglement challenges classical causality, and how some interpretations of quantum theory describe a timeless universe beneath probabilistic outcomes. For now, it is enough to recognize this: the direction of time is not a fundamental law. It is a story written by entropy, and like all stories, it depends on how it begins. Time inside the quantum world. So far, time has already lost much of its certainty. It can slow down, stretch, disagree between observers, and take its direction from entropy rather than law. But the deepest challenge to time does not come from the very large. It comes from the very small. At the quantum level, the idea of a smooth flowing time begins to fracture. Quantum mechanics describes the behavior of particles, fields, and interactions at the smallest scales. It is one of the most successful theories ever created, predicting experimental results with extraordinary precision. And yet, its relationship with time is deeply strange. In standard quantum mechanics, time is treated differently from space. Space isn't observable. Particles can be in multiple positions at once, spread out as probability waves. Time, however, is not something a particle can be in multiple values of. Time is treated as an external parameter, a background clock against which change is measured. This asymmetry has always been uncomfortable. If space and time are unified in relativity, why does quantum mechanics treat them so differently? Why can position be uncertain while time must remain fixed? Why is there no operator for time in the same way there is for momentum or energy? These questions do not break quantum mechanics, but they hint that something deeper is missing. The strangeness becomes more apparent when we consider quantum superposition. A particle can exist in multiple states at once until it is measured. In some sense, the particle does not choose a definite outcome until interaction forces it to. This already challenges classical ideas of cause and effect. Now, imagine trying to assign a clear temporal order to events inside a quantum system. In certain quantum experiments, it becomes impossible to say which event happened first. Not just difficult, but fundamentally undefined. The order of interactions can exist in a superposition, where event A happens before event B, and event B happens before event A at the same time. This is not a limitation of measurement, it is a feature of the theory. These phenomena suggest that time ordering, so essential to our everyday experience, may not exist at the quantum level in the way we expect. The universe, at its smallest scales, may not care about before and after. Entanglement deepens this mystery. When two particles become entangled, their states become correlated no matter how far apart they are. Measuring one instantly determines the state of the other, even across vast distances. This does not allow faster-than-light communication, but it does create correlations that seem to ignore spatial separation and temporal separation as well. In some interpretations, entangled particles are not separate objects at all. They are parts of a single quantum state. If that is true, then asking which measurement happened first may be meaningless. The system exists as a whole, outside simple temporal ordering. This pushes us toward a radical thought. Perhaps time, like classical trajectories, is something that emerges only when quantum systems interact with large environments. When a quantum system becomes entangled with its surroundings, superpositions collapse into definite outcomes. This process, often described as decoherence, gives rise to classical behavior. It turns probabilities into apparent certainties, and with that transition, time may emerge. In this view, time is not fundamental at the quantum level. It appears only when systems become large enough, complex enough, and sufficiently entangled with their environments to behave classically. Time would then be a macroscopic phenomenon. This idea is supported by approaches to quantum gravity, where space-time itself is expected to break down at very small scales. If space-time is not fundamental, then time, being part of space-time, cannot be fundamental either. Instead, the deepest description of reality may involve timeless relationships between quantum states. This does not mean nothing happens. It means that happening may not require time in the way we imagine. Change could be encoded as correlations within a static structure. Some physicists describe this as a universe where everything exists all at once, but not in a simple block universe sense. Instead, the universe is a network of quantum relations, where what we perceive as temporal evolution is our way of navigating that network. In such a universe, time is not the stage on which events occur. It is the map we draw to make sense of correlations. This becomes clearer when we consider how time is actually measured in quantum systems. There is no universal quantum clock. Instead, time is defined relationally. One system is used as a clock to measure change in another system. A vibrating atom, a decaying particle, or an oscillating field serves as a reference. Time is always something measured against something else. If you remove all clocks, all change becomes unordered. The system still exists, the relationships still exist, but time loses its meaning. This suggests that time is not an independent entity, it is a way of comparing changes. Quantum mechanics seems to whisper this idea quietly but persistently. The universe does not need time to exist, it needs relationships. And once again, time looks less like a foundation and more like a tool. As we move forward, we will see how this timelessness becomes unavoidable when physicists attempt to describe the universe as a whole, especially in theories where space and time themselves are emergent rather than fundamental. Because if time disappears at the smallest scales and stretches at the larger scales, then the time we experience may exist only in a narrow window in between, a window we happen to occupy. When the universe has no clock. The idea of a timeless universe sounds abstract until physics forces it into focus. That moment arrives when scientists attempt to write equations that describe the universe as a whole. Not a part of the universe, not particles inside it, the universe itself. In everyday physics, time is provided externally. You write equations that describe how a system evolves as time passes. But when the system you are describing is the entire universe, there is nothing outside it to supply that time. There is no external clock. This is where the problem of time becomes unavoidable. In attempts to unify general relativity and quantum mechanics, physicists derive equations that describe the quantum state of the universe, and again, time refuses to appear. The Wheeler-DeWitt equation is the most famous example. It is often described as the equation for the universe, and it has no time variable. The equation does not say how the universe changes over time, it simply describes allowed configurations. From the equation's perspective, the universe does not evolve. It exists. This result is not a mistake. It emerges naturally from the mathematics, and it forces a profound question. If the universe does not evolve in time at the deepest level, then what does evolution mean? One response is to say that time is hidden, that it exists, but in a form we have not yet recognized. Another response is more radical. Time is not there to be found. Instead, time emerges when parts of the universe observe other parts. In this picture, there is no global time. There are only local times, defined by subsystems acting as clocks for each other. One part of the universe changes relative to another, and we interpret that change as temporal evolution. Time becomes relational. This idea has deep roots. Even in classical physics, time is measured by motion. A clock is just a system that changes predictably. Quantum gravity takes this idea to its extreme. The universe contains no master clock. All clocks are internal. If you choose one part of the universe as a clock, you can describe how other parts change relative to it. Choose a different clock, and you get a different description. None is more fundamental than the others. This challenges the idea of a single cosmic timeline. It suggests that the universe is more like a collection of interrelated processes than a story unfolding in time. This is deeply counterintuitive because our minds are built to experience sequences. We think in narratives. We expect beginnings, middles, endings, and ends. A timeless universe does not offer that structure naturally. Yet the mathematics remain stubborn. Some physicists describe this situation by saying that the universe is frozen at the deepest level. Not frozen in the sense of inactive, but frozen in the sense that it is not evolving with respect to any external time. All change is internal. From within the universe, observers like us experience time because we are part of subsystems that change relative to each other. Our brains track patterns. Our memories store records. Our bodies process energy. These processes create the feeling of flow, but the universe as a whole does not need to flow. This idea reshapes the meaning of cosmology. Instead of asking how the universe evolves in time, we ask how time emerges from the universe. Cosmic expansion, for example, may not be something that happens over time in a fundamental sense. It may be a relationship between different configurations of the universe that we order temporally because of how we observe them. Even the Big Bang may not be a moment in time in the deepest description. It may be a boundary condition, a feature of the universe's structure rather than a starting gun. This is why asking what happened before the Big Bang becomes problematic. If time emerges with the universe, then before has no meaning. Some models go further and suggest that different regions of the universe could experience time differently, or that time itself could emerge in multiple ways depending on local conditions. In such a universe, time is not a universal river, it is a patchwork. This does not make time unreal in the everyday sense. We still wake up, grow older, remember, and anticipate. But it does suggest that time is not written into the universe at the deepest level. It is written into us. The universe may be a static structure rich with relationships, while time is the way conscious systems move through those relationships. This idea is unsettling because it removes time from its privileged position. It turns time into something like temperature, real, measurable, important, but emergent rather than fundamental. And like temperature, time may disappear when the conditions that create it disappear. As the universe evolves toward higher entropy, toward fewer gradients and fewer changes, time may become less meaningful. Not because clocks stop ticking, but because nothing significant changes. In that distant future, if such a future exists, the universe would still be there. But time, as we experience it now, might not be. This is the quiet implication of a universe with no clock. Time may not be something the universe contains, it may be something the universe allows. Why time feels so real? If time may not be fundamental, if it can disappear from the deepest equations and fracture at the smallest scales, then a natural question follows. Why does time feel so overwhelmingly real? Not abstractly real, not mathematically real, but personally real. You feel time passing, you feel the weight of duration, you feel the difference between waiting and remembering. No theory can simply dismiss that experience. Any serious account of time must explain why it feels the way it does. The answer may lie not in the structure of the universe, but in the structure of minds. Human consciousness is built around change. Every sensation you have depends on difference. Light changing across the retina, sound waves shifting air pressure, chemical signals rising and falling in the brain. A completely unchanging environment would be indistinguishable from no environment at all. Because of this, consciousness does not register static reality. It registers transitions. Time from this perspective is not something you observe directly. It is something you infer from change. Your brain is constantly comparing states. What just happened versus what is happening now. That comparison creates a sense of sequence. Sequence creates duration. Duration creates the feeling of time flowing. This process happens so smoothly that it feels immediate and unavoidable. But it is not guaranteed by physics. It is generated by cognition. Memory plays a central role here. To experience time as flow, you must remember the immediate past. Without memory, there is no sense of continuity. Each moment would stand alone, unconnected to the next. Time would collapse into a series of unrelated flashes. Memory binds moments together. It allows the brain to construct a narrative. And narratives require order. But memory is not neutral. It only works in one direction. You remember lower entropy states. You remember what has already happened. You do not remember the future because there are no records of it yet. This asymmetry is not psychological accident. It is thermodynamic necessity. Creating memory requires energy. Energy use increases entropy. This means memory formation can only happen in the direction in which entropy increases. Your experience of time's direction is therefore locked to the arrow of entropy. This suggests that the psychological arrow of time, the feeling that time flows forward, is not imposed by the universe. It is imposed by the way memory works in physical systems like brains. This also explains why time feels smooth. The brain does not process reality in discrete snapshots. It integrates information over short intervals, smoothing transitions. What you experience as a continuous present is actually a construction, a blending of recent moments into a coherent now. Neuroscience suggests that the present moment you feel may span several seconds of neural processing. Your awareness is slightly delayed, slightly averaged, and constantly updated. Time feels like a flowing river because the brain is constantly updating its internal model of the world. In this sense, time is not something you move through. It is something your brain assembles. This idea becomes even more striking when we consider altered states of consciousness. Under stress, time can feel slow. During absorption or focus, hours can feel like minutes. In dreams, time can distort or collapse entirely. In certain neurological conditions, the sense of temporal order can break down. These changes do not reflect changes in the universe. they reflect changes in how the brain processes information. This strongly suggests that time, as experienced, is not a direct readout of reality. It is an interface. The philosopher William James once described time as the short duration of which we are immediately and incessantly sensible. Modern neuroscience echoes this idea. The brain constructs time locally, moment by moment, based on change and memory. If the universe were truly timeless at its deepest level, conscious systems would still experience time as long as they processed information asymmetrically. This means time can feel real, even if it is not fundamental. This also helps explain why the block universe feels unsettling. If all moments exist equally, why do we feel as if we are moving? Because movement is not happening in space-time. It is happening in mental state space. Your brain occupies one configuration, then another, then another. Those configurations are ordered by memory and entropy. From the inside, this feels like motion through time. From the outside, it may simply be a sequence of correlated states. This reframing does not deny experience. It explains it. Time feels real because experience requires order. Order requires memory. Memory requires entropy increase. And entropy increase gives time its arrow. This also suggests that if there were conscious beings in a different entropy gradient, hypothetically experiencing entropy decrease, they might experience time in the opposite direction. Their memories would point the other way. Their sense of cause and effect would be reversed. From their perspective, they would be normal. From ours, they would appear to be remembering the future. Such ideas are speculative, but they reveal how deeply experience is tied to thermodynamics rather than to time itself. The feeling of now is particularly revealing. Physics has no special place for the present moment. There is no equation that marks one slice of space-time as now, and yet consciousness insists on it. The present is where memory ends and anticipation begins. It is the boundary between stored information and uncertainty. This boundary exists in the brain, not in space-time. The present moment is not a feature of the universe. It is a feature of information processing. This idea does not make time meaningless. It makes it local. Time is real where minds exist. It is vivid where memory and change intersect. It fades where systems reach equilibrium. This may be why time feels so intense during life and so absent in deep sleep or unconsciousness. When memory and perception pause, time loses its grip. In the deepest sense, time may be a relationship between consciousness and change. The universe may not care about time, but conscious systems do. As we continue, we will explore what this means for the origin of time, the beginning of the universe, and whether time could emerge differently or not at all in other regions of reality. Because if time is something that happens when the universe is observed from within, then the question is not, is time real? The question becomes, under what conditions does time appear? And could those conditions ever disappear? Did time have a beginning? Once time stops looking fundamental, the question of its origin becomes unavoidable. If time is something that emerges, then there must have been a moment, if that word still applies, when time was not yet present. This turns one of the most familiar questions in cosmology into something far stranger. Not how did the universe begin, but how did time begin? In everyday thinking, beginnings are events that happen at a moment in time. A story starts on the page 1. A race begins at a starting line. A life begins at birth. But if time itself has a beginning, then there was no earlier moment for it to begin in. There was no ticking clock waiting for the universe to start. This is where language starts to strain. In standard cosmology, the Big Bang is often described as the beginning of time. Not an explosion in space, but the origin of space and time together. As we trace the universe backward, distances shrink, temperatures rise, and eventually the equations point toward a boundary, a point where our description of space-time breaks down. At that boundary, time seems to lose meaning. If time is part of space-time and space-time itself emerges from that boundary, then asking what happened before the Big Bang may be like asking what is north of the North Pole. The question assumes a framework that no longer applies, but this explanation, while elegant, may not be the final word. Some physicists argue that what breaks down at the Big Bang is not reality, but our theory. General relativity, which describes space-time as smooth and continuous, is known to fail at extremely small scales. Quantum effects become dominant, and space-time itself may behave very differently. In that quantum gravitational regime, time may not vanish entirely, it may exist in a different form. Several models attempt to describe this. In some approaches, the Big Bang is not a beginning but a transition. A previous phase of the universe contracts, reaches a minimum size, and then expands again. In such models, time may extend through the bounce, but its direction could reverse relative to entropy. From each side of the bounce, time would appear to flow away from the low entropy point. This leads to a universe with two arrows of time pointing in opposite directions. From our perspective, the past is toward the bounce. From the other side, what we call the future would be their past. Both sides would experience time as flowing forward, even though they move away from the same boundary. If such a universe exists, then time did not begin. It branched. Other models suggest that time emerges gradually. In the earliest phase of the universe, conditions were so extreme that the distinction between time and space dissolved. Instead of one time dimension and three space dimensions, there may have been four space-like dimensions, or a fluctuating mixture of both. As the universe cooled and expanded, one dimension may have become time-like, allowing a stable notion of causality to emerge. In this view, time did not appear suddenly, it crystallized. This idea has a subtle implication. If time emerged as the universe cooled, then the earliest universe may have existed in a timeless or quasi-timeless state. Not frozen, but unordered in a way that does not allow a clear sequence of events. Only when the universe entered a regime where entropy gradients could form did time, as we know it, begin to make sense. This connects time's origin directly to entropy. If time's arrow depends on low entropy, then the beginning of time may be defined not by geometry alone, but by the emergence of order. The moment when the universe became special enough to support gradients, memory, and records may be the moment time began to feel real. This reframes the Big Bang. Instead of a singular instant that started everything, it becomes a boundary between a timeless description and a time-ordered one. On one side, the universe is described by static relationships. On the other, those relationships can be ordered into a sequence. Time, then, is not the first thing, it is the first interpretation. This perspective also helps explain why the early universe appears so simple. Observations show that it was remarkably uniform and low in entropy. That simplicity may not be an accident. It may be the condition that allowed time to exist at all. Without that simplicity, entropy gradients could not form. Without gradients, no arrow. Without an arrow, no experienced time. So the beginning of time may coincide with the beginning of structure. There are even more radical ideas. Some physicists propose that time is an emergent statistical phenomenon similar to temperature. Temperature does not exist for a single particle. It exists for large collections of particles. Likewise, time may not exist for the universe as a whole at the smallest scales. It may exist only when many degrees of freedom interact. In such models, asking when time began is like asking when temperature began in a gas. There is no sharp moment. There is a transition as complexity increases. This would mean that time did not turn on. It faded in. These ideas are difficult to test directly, but they align with a broader pattern in physics. Many things that feel fundamental turn out to be emergent. Solidity, color, pressure, and even space itself can arise from deeper interactions. Time may belong to that list. This does not diminish its importance. Emergent phenomena can be incredibly powerful. Weather is emergent. Life is emergent. Consciousness is emergent. None of these are illusions, but they depend on conditions. If the conditions change, the phenomenon changes or disappears. This raises a quiet possibility about the far future of the universe. If time emerged when the universe was far from equilibrium, what happens when the universe approaches equilibrium again? As stars burn out and matter spreads thin, entropy increases, gradients flatten, change slows. In that distant future, time may still exist mathematically, but experientially it may become empty. There may be nothing left to mark its passage. In that sense, time may have both a beginning and an end, not because the universe stops existing, but because the conditions that give time meaning cease. This idea is unsettling, but also strangely consistent. Time begins when the universe becomes interesting enough to remember. Time ends when the universe becomes too uniform to change. Between those two states lies everything we experience. As we continue, we will explore how this view of time affects our understanding of causality, free will, and the idea of choice. If the universe is timeless at its core, what does that mean for decisions, responsibility, and the sense that we could have done otherwise? Because questioning time inevitably leads to questioning what it means to act within it. Cause, effect, and the illusion of choice. If time is not fundamental, then causality, our sense that one thing causes another, also begins to feel less secure. Cause and effect seem inseparable from time. A cause must come before an effect. A decision must precede an outcome. Remove time, and the structure that supports choice appears to weaken. And yet causality persists in our experience as strongly as time itself. Everyday life feels driven by decisions. You choose, then something happens. You act, then consequences follow. This sequence is so deeply embedded in human thinking that it forms the basis of responsibility, intention, and meaning. But physics, once again, tells a quieter and more complicated story. In fundamental equations, especially those that are time-symmetric, causality is not written in the same way we experience it. The equations describe relationships between states, not arrows pointing from cause to effect. They allow events to be ordered in time, but they do not require a preferred direction. This suggests that causality, like time's arrow, may be emergent rather than fundamental. At the microscopic level, many processes do not clearly distinguish cause from effect. In quantum mechanics, correlations can exist without a clear causal chain. Entangled particles influence outcomes together, not sequentially. In some interpretations, the universe does not decide outcomes until observation, and even then, the notion of cause becomes subtle. This has led some physicists and philosophers to argue that causality is a macroscopic pattern, a way of summarizing regularities that emerge when many events are considered together. In this view, causality is not a rule imposed by the universe. It is a story that works because the universe behaves consistently. Time plays a role in making that story feel solid. Because entropy increases, information flows in one direction. Records form of past states, not future ones. This gives the appearance that causes precede effects. But if we step back and view the universe as a block, a complete structure of events, then cause and effect may simply be different ways of slicing that structure. From this perspective, choices do not create the future. They are part of the structure that includes both the choice and its outcome. This idea often raises concerns about free will. If the future already exists, if all moments are laid out in space-time, then what does it mean to choose? Physics does not answer this directly, but it reframes the question. In a block universe, choices are real events. They exist as part of the structure. What disappears is the idea that the future is open in a fundamental sense. Instead, openness may be a feature of experience rather than reality. You do not know the future. That ignorance is genuine. It shapes your decisions. From your perspective, multiple outcomes are possible. That perspective is enough to give meaning to choice, even if, from a timeless view, the outcome is fixed. This is similar to reading a book you have not finished. The ending exists, but you do not know it. Your experience of suspense, decision, and consequence remains real. This does not make free will an illusion. It makes it local. Choice exists where information is incomplete, where entropy hides future states, where memory points one way and uncertainty points the other. Causality in this sense is an emergent pattern that allows complex systems to function. Brains predict outcomes. Bodies act on those predictions. Societies coordinate behavior based on expectations of cause and effect. None of this requires time to be fundamental. It requires consistency. The universe, whatever its deepest structure, is consistent enough that patterns repeat. Those patterns allow us to speak meaningfully about cause, effect, and responsibility. Quantum mechanics adds another layer to this story. In some interpretations, outcomes are not determined until measurement. This introduces a kind of indeterminacy that seems to restore openness to the future. But even here, time plays a subtle role. The equations that govern quantum systems evolve deterministically. Probability enters when systems interact with environments and observers. The randomness appears not as a violation of time symmetry, but as a feature of how the information becomes classical. Whether this randomness restores free will or simply adds noise is still debated. But it reinforces the idea that time and causality are not simple one-layer concepts. They are structures built from deeper processes. If time is emergent, then causality likely emerges alongside it. Both arise from entropy gradients, information flow, and the way complex systems store records. This makes causality robust where those conditions exist, and fragile where they do not. Near equilibrium, where little changes, cause and effect become hard to define. In deeply quantum regimes, where events lack definite order, causality blurs. In everyday life, where entropy's gradients are strong and memory is reliable, causality feels absolute. This gradient-dependent nature of causality mirrors the gradient-dependent nature of time. Neither may be fundamental. Both may be consequences of the universe being in a particular state. This does not diminish their importance. It explains their reliability. We trust cause and effect because the universe has been consistent enough for trust to evolve. But consistency does not require time to flow. It requires relationships to hold. This perspective allows us to keep meaning without insisting on metaphysical privilege. We can accept that time and causality are real where we live, without demanding that they be written into the universe's deepest equations. As we move on, we will examine what happens when time is treated explicitly as an illusion, or at least as a derived concept, and how different theories attempt to rebuild reality without it. Because once time loses its foundational status, physics faces a strange task, explaining a world that appears to change using rules that do not include change at all. A universe without before and after. To imagine a universe without time is to imagine a reality without before and after. This sounds impossible because language itself is built on sequence. Every sentence unfolds. Every thought has order. To describe a timeless universe, we must constantly borrow the very concept we are trying to set aside, and yet physics continues to point in that direction. When time disappears from the deepest equations, what remains is not chaos. What remains is structure. Relationships, constraints, patterns that do not evolve but simply are. In such a universe, the fundamental description does not say what happens next. It says what configurations are allowed. This is a profound shift in how explanation works. Instead of asking why the universe changes the way it does over time, we ask why the universe has the structure it has at all. The question becomes geometric rather than dynamic. This view is not entirely new. Even classical mechanics can be described in a timeless way using principles like least action. Instead of tracking motion moment by moment, these formulations describe entire paths at once. The path the system takes is the one that satisfies certain constraints, not one that is pushed forward by time. Quantum mechanics, too, often works this way. Path integrals consider all possible histories at once, assigning probabilities to entire trajectories rather than single moments. These approaches hint that time may be a convenient parameter rather than a fundamental driver. In a timeless universe, what we call change is a comparison between different parts of a static structure. One configuration differs from another. When an observer is part of that structure, they experience those differences as temporal progression. This does not require time to exist as a flowing entity. It requires correlation. Imagine a landscape of states, each connected to others by rules. Moving through that landscape is not something the universe does. It is something an observer does by being embedded in one region of the landscape rather than another. This idea reframes existence itself. The universe does not unfold. It exists all at once. What unfolds is perspective. This may explain why time is so difficult to detect directly. We do not measure time itself. We measure change. We count oscillations, we observe decay, we track motion. Time is inferred. If the universe were perfectly static, time would vanish, not because it is hidden, but because it would have no meaning. This also sheds light on why the present moment feels special, even though physics does not privilege it. The present is where correlations are accessible. It is where information is locally available. The past exists as records. The future exists as constraints. The present is where computation happens. In a timeless universe, now is not a slice of space-time. It is a state of knowledge. This idea has implications beyond physics. It touches philosophy, consciousness, and the nature of explanation itself. If the universe does not change, then explanation does not run from past to future. It runs from structure to experience. Why does the universe appear dynamic? Because observers inside it experience sequences of correlated states. Why does time feel continuous? Because cognitive systems smooth transitions. Why does the future feel open? Because information about it is inaccessible. None of these require time to be fundamental. They require limits on information. This perspective is unsettling because it removes the comfort of flow. It replaces the story of becoming with a picture of being. But it also offers a strange kind of peace. If all moments exist, then nothing is truly lost. The past is not gone. It is simply not where you are. This idea has been explored not only in physics, but in philosophy and even in literature. It challenges the assumption that meaning depends on change. Meaning may instead depend on relationships. In such a universe, the role of physics is not to describe motion, but to describe possibility. The universe is a space of allowed configurations. Time is how we navigate it. This does not mean physics is finished with time. It means time may not be where we thought it was. As we approach the final chapters, we will ask what all of this means for our place in the universe. If time is emergent, local and perspective dependent, how should we think about our lives, our histories, and our futures? Is the disappearance of time a loss of meaning or a shift in where meaning lives? Because if time is not real in the deepest sense, then what remains may be more subtle, more relational, and perhaps more enduring than we ever expected, living inside a timeless universe. If the universe is timeless at its deepest level, then the most surprising fact is not that time disappears from equations, it is that beings like us can exist at all. We live inside a structure that may not fundamentally change, yet our lives are defined by change. We grow, remember, decide, and imagine futures. How can such experiences arise inside a universe that, in some sense, simply is? The answer may be that life does not require time to be fundamental. It requires difference. Living systems are not static objects. They are processes, patterns that persist by constantly transforming energy and matter. A flame exists only while fuel flows. A heartbeat exists only while chemical gradients are maintained. Life is not a thing located in time. It is a pattern sustained by imbalance. This is crucial. A timeless universe can contain patterns that from the inside experience sequence. Those patterns do not need time to move forward. They only need to occupy a series of related sets. From an external description, those states coexist as part of a structure. From an internal perspective, they are lived as moments. In this way, life becomes the bridge between timeless structure and temporal experience. Consider how biological time works. Cells divide, organisms age. These processes are driven by thermodynamics, not by a cosmic clock. Chemical reactions proceed because they lower free energy. Damage accumulates because entropy increases. Repair systems slow over time because gradients weaken. Aging is not caused by time passing, it is caused by entropy accumulating. We measure aging in years, but the years are not the cause. They are the accounting system. This reframing shifts how we think about existence. Instead of seeing ourselves as passengers carried along by time, we become systems evolving through state space. Each moment is a configuration. The feeling of movement comes from how those configurations are ordered by memory. This also changes how we think about the future. In everyday life, the future feels open. We plan, we hope, we fear. But in a block universe or timeless framework, the future may already exist as part of the structure. That does not mean it is accessible. It means it is not created by motion. From inside the system, ignorance remains real. You do not know what happens next. That uncertainty shapes behavior. Decisions still matter because they are part of the structure that includes outcomes. Meaning survives not because the future is undetermined, but because it is unknown. This is a subtle but powerful distinction. It suggests that meaning does not require metaphysical openness. It requires informational openness. As long as systems cannot access future states, they will behave as if multiple outcomes are possible. That behavior is enough to support responsibility, creativity, and intention. Time then becomes the language systems use to describe their own limitations. We say later because we do not yet have access. We say past because we have records. We say now because this is where computation happens. This perspective also explains why time feels personal. Each observer has their own history of records. Each brain has its own chain of memories. There is no shared present because there is no shared access to information. Time becomes local not only in physics, but in experience. This locality does not isolate us. It connects us through interaction. When systems interact, they exchange information. Their timelines partially align. Shared experiences emerge. This is why coordination is possible. It is why societies exist. It is why science works. Time may not be fundamental, but synchronization is. We synchronize clocks, not because time exists independently, but because coordination requires agreed-upon references. Timekeeping becomes a social technology layered on top of physical processes. Even physics uses clocks operationally. Time is defined by what clocks do, not by an independent entity, and seen this way, time becomes a powerful abstraction, a tool that allows complex systems to model change efficiently. Abstractions are not illusions, they are compressions of reality. They allow finite systems to navigate infinite structure. The danger comes when abstractions are mistaken for foundations. Physics may be discovering that time is one of those abstractions, that discovery does not make life emptier. It makes it more precise. It tells us that what we value, experience, memory, meaning, does not depend on the universe flowing, it depends on how we exist within it. If the universe is timeless, then our lives are not fleeting moments swept away. They are patterns that exist as surely as any mountain or galaxy. They do not vanish, they simply are not where we are anymore. This thought can feel unsettling, but it can also feel grounding. It suggests that existence is not fragile in the way we imagine. Change does not erase what was, it rearranges perspective, and perspective is where life lives. As we approach the final chapter, one question remains. If time is emergent and perspective-bound, is it meaningful to say that time is not real? Or is that question itself misplaced? Because perhaps the deepest lesson is not that time is unreal, but that reality is larger than time. The quiet answer. After tracing time through relativity, quantum mechanics, entropy, consciousness, and cosmology, the question that remains is not a scientific one. It is a conceptual one. When we ask whether time is real, what do we mean by real? If we mean fundamental, physics offers reasons to doubt. Time bends, stretches, disappears from equations, and may emerge only under certain conditions. At the deepest levels, the universe may be describable without reference to time at all. But if we mean experienced, the answer is undeniable. Time shapes every thought, every memory, every decision. It organizes life. It gives structure to meaning. Both of these truths can coexist. Time may not be fundamental to the universe, but it is fundamental to us. This distinction resolves much of the tension. Physics is not trying to erase experience, it is trying to understand structure. When time disappears from equations, it is not because time is an illusion, but because the equations are describing a level of reality where experience does not operate. At that level, there are no observers, no memories, no records. There are only relationships. Time emerges when relationships become complex enough to support information flow in one direction. This makes time contextual rather than absolute. It exists where conditions allow it. It fades where they do not. This is not a weakness in our understanding, it is a refinement. The universe is not required to mirror human intuition. Human intuition evolved to navigate a narrow band of conditions: moderate speeds, weak gravity, strong entropy gradients. Outside that band, intuition fails. Physics extends understanding beyond that band. When it does, it often reveals that familiar concepts are approximations. Space, solidity, temperature, and now time all turn out to be emergent. Emergence does not mean false, it means layered. The surface of a lake is real, so are the molecules beneath it. One does not cancel the other. Time may be like that. At the deepest level, the universe may be timeless. At the level of experience, time is unavoidable. This layered view allows us to keep both wonder and rigor. It allows us to say that time might not be real in the way we once thought, while still honoring the reality of living within it. Perhaps the quiet answer is this: time is not what the universe uses to exist. Time is what existence uses to be understood. The universe does not rush forward. It does not wait. It does not age. But within it, patterns arise that can remember, anticipate, and wonder. Those patterns call what they experience time, and for them, for us, that is enough. If there is peace to be found in this idea, it is not in denying time, but in loosening its grip. The moment you are in is not racing away. It is one of many moments that exist as part of a larger whole. You are not being carried forward. You are already where you are, and in a universe that may be timeless, that may be the most grounded place to rest. If time is not real, what is? When a concept dissolves at the deepest level of physics, it leaves behind a silence that feels uncomfortable. Time has been with us for as long as thought itself. It orders language, memory, identity, and meaning. To imagine reality without it feels like removing the floor from beneath understanding. And yet, when time loosens its grip, something else becomes clearer. What remains is not chaos. What remains is relation. At the deepest level described by modern physics, reality appears less like a story unfolding and more like a structure that simply exists. Not frozen, not static in the everyday sense, but complete. A web of relationships where nothing needs to move forward for everything to be connected. In such a picture, the universe is not defined by change, but by possibility. States exist, constraints exist, correlations exist. What we call events are points of connection within this structure. What we call change is the comparison between different configurations. Time is the tool that allows finite minds to navigate that structure. This reframing shifts the focus from becoming to being. The universe is not constantly arriving somewhere else. It already contains every configuration allowed by its laws. What varies is where attention is located. This does not make reality cold or indifferent. It makes it vast. If time is emergent, then meaning does not come from duration. It comes from structure and relationship. A moment does not matter because it passes. It matters because of how it relates to other moments. Music is not meaningful because notes disappear. It is meaningful because of how notes are arranged. A melody exists as a whole even though it is experienced sequentially. The universe may be more like music than motion. In this sense, asking whether time is real may be the wrong question. A better question is whether time is the only way to understand reality. Physics suggests it is not. There may be descriptions of the universe where time plays no role at all. Descriptions that speak only of constraints, symmetries, and relationships. These descriptions are not meant to replace experience, they exist alongside it. We live inside one layer of reality. Physics tries to describe many. This layered view dissolves a false conflict. Time does not have to be either real or unreal. It can be real where it appears and absent where it does not. Pressure is real in gases but meaningless in a vacuum. Temperature is real in crowds of particles but undefined for one. Time may be similar, real in complex information processing systems, undefined in the deepest description of the universe. If so, then the question "is time real?" becomes contextual. For the universe as a whole, perhaps not. For life, absolutely. This also reframes mortality. If all moments exist as part of a structure, then nothing is truly erased. The past is not destroyed, it is simply not where perspective is currently located. This does not mean memory survives independently. It does not promise continuity of awareness. But it does suggest that existence is not as fragile as flow makes it seem. Moments do not vanish. They remain as relations. This idea has quietly appeared across disciplines, physics, philosophy, even ancient contemplative traditions. Again and again, the suggestion arises that reality is not fundamentally a river, but a field. A field does not move forward. It contains patterns. Time may be the pattern we use to read the field from inside. As this journey nears its end, it becomes clear that the mystery of time is not a failure of understanding. It is a sign that understanding has limits and layers. We use time because it works. Physics questions time because it must. Both are true. The universe does not owe us intuitive foundations. It offers structure. We bring interpretation. And in that interpretation, time emerges, not as an illusion, but as a bridge between timeless reality and lived experience. Time, language, and the limits of description. Even after everything we've explored, one obstacle remains quietly in place: language. Nearly every word we use assumes time. Verbs have tenses, sentences unfold. Meaning depends on sequence. When we try to describe a timeless reality, we are forced to use tools that were built for a temporal one. This is not a flaw in language. It is a reflection of how language evolved. Language evolved to coordinate action, memory, and expectation among beings living inside strong entropy gradients. It is designed to describe what happened, what is happening, and what might happen. It is not designed to describe a structure that exists all at once. This is why discussions of time often feel paradoxical or circular. We try to step outside time using concepts that only make sense inside it. Physics faces the same challenge. Equations are written as relationships, but we interpret them as processes. We speak of evolution, change, and dynamics even when the mathematics itself does not require a flowing parameter. This can make timeless theories feel incomplete, even when they are internally consistent. When physicists say that time disappears from an equation, they do not mean that experience vanishes. They mean that the equation describes a level of reality where description no longer depends on sequence. This gap between description and experience is not something to be resolved. It is something to be navigated. It reminds us that no single perspective captures all layers of reality. The view from within is different from the view from without. Both are valid within their domains. Language, like time, may be emergent. It compresses reality into manageable forms. It allows finite minds to operate in an infinite structure. When we say time passes, we are not making a metaphysical claim. We are using a tool that works. Physics, when it questions time, is not denying experience. It is refining description. These two activities can coexist without contradiction. The universe does not need to be described the same way at every level. What matters is that the descriptions are consistent where they overlap. Time works extraordinarily well where we live. It organizes memory, causality, and coordination. It becomes questionable only when we push beyond the conditions that give it meaning. This is not a failure of time. It is a success of context. Perhaps the deepest lesson here is humility. The universe is under no obligation to match the categories our minds prefer. When those categories begin to fail, it is not reality that is breaking. It is our expectations. Time may be one of the most useful expectations we have ever formed. That usefulness does not require it to be fundamental. The calm that remains. After questioning something as basic as time, it is natural to expect discomfort. And yet many people find the opposite. There is a calm that settles in once the idea fully lands. If time is not a relentless current pulling everything away, then existence feels less fragile. Moments do not have to be defended against disappearance. They do not have to be held tightly. They exist as part of a larger structure, connected, complete, and unmoving at the deepest level. From this perspective, change is not loss. It is perspective shifting. You are not losing moments as they pass. You are moving attention through a landscape of relations. The moments you remember are not gone. They are simply not where your attention is now. This does not remove sadness or longing or the poignancy of change, but it softens the fear beneath them. It suggests that meaning does not depend on duration, it depends on relation. A short life can be complete, a brief moment can be entire. What matters is not how long something lasts, but how it fits into the structure around it. This idea resonates quietly with many human traditions, not because they anticipated modern physics, but because they were responding to the same intuition that reality is deeper than motion, and that stillness is not emptiness. Physics arrives here not through meditation, but through mathematics. The path is different. The destination feels familiar. Time then becomes something like a lens. It allows us to see reality in a way that is useful for living. But it is not the only lens. When you relax the assumption that everything is rushing forward, attention changes. The present moment feels less like a knife edge and more like a place, not a fleeting instant, but a location in experience. This does not stop clocks, it does not undo aging, but it changes the story we tell about them. You are not racing against time, you're participating in a structure that allows time to appear, and when the universe is seen that way, there is nothing urgent about existence, there is only presence. In a reality that may be timeless at its deepest level, calm is not something you create, it is something you remember. The question we stop asking. At some point in every deep inquiry, the most important shift happens quietly. It is the moment when the question itself changes. At the beginning of this journey, the question was clear and unsettling. Is time real? It feels sharp, provocative, almost dangerous to ask. But after moving through relativity, quantum mechanics, entropy, consciousness, and cosmology, that question begins to soften. It starts to feel less like a problem to be solved and more like a doorway into a different way of seeing. Because what physics keeps revealing is not that time is an illusion in the everyday sense, but that reality is layered. And time belongs to one of those layers, not the deepest, not the shallowest, but one that is perfectly tuned for beings like us. Time is where experience lives. It is where memory organizes itself, where cause and effect become useful, where choice feels meaningful, where stories can exist at all. A universe without time may be mathematically complete, but it would be experientially silent. And so the question quietly becomes something else. Not, is time real? But why does reality allow time to appear at all? That is a much gentler question. It suggests that time is not a flaw or a mistake, but a feature that emerges when the universe becomes rich enough to observe itself. When information flows asymmetrically, when records form, when patterns can reflect on other patterns. Time may be the universe's way of becoming understandable from the inside. This reframing dissolves a common fear, that if time is not fundamental, then meaning is threatened. In fact, the opposite may be true. Meaning may depend on time being local rather than absolute. If time were universal and fixed, experience would be rigid. If time were fundamental and unstoppable, existence might feel mechanical. Instead, time bends, stretches, slows, fragments, and sometimes disappears, creating room for perspective. Perspective is where meaning lives. Physics, at its deepest, may describe a universe that simply exists. But life is not lived at that level. Life is lived at the level where distinctions matter, where one state differs from another, where memory has direction, and where uncertainty still exists. And time is the name we give to that level. This does not make time arbitrary, it makes it appropriate. It is exactly as real as it needs to be. When physics strips time from its deepest equations, it is not telling us that time is false. It is telling us that time is not the foundation. Foundations do not feel, they do not remember, they do not wonder. We do. And so the final lesson of this journey is not about denying time, but about placing it gently where it belongs. Not as the ruler of reality, but as one of its expressions. Time is what reality feels like when experienced from within, and perhaps that is enough. Time and the shape of reality. When physics questions time, it often replaces it with something quieter, structure. Instead of asking how reality changes, it asks how reality is arranged. This shift may be one of the most important conceptual moves in modern science. In many fundamental theories, reality is described not as a sequence of moments, but as a configuration space, a vast landscape of possible states. Each state is complete in itself. Nothing happens inside a state. What we call motion or change is the comparison between states. From this perspective, time is not the driver of reality. It is the coordinate we use to move through that landscape. This idea appears in multiple places across physics. In relativity, space-time is already a fixed geometric object. In quantum mechanics, systems are often described by wave functions that encode all possible outcomes at once. In quantum gravity, space-time itself may be emergent from more basic relationships. What unites these approaches is the suggestion that reality has a shape before it has a story. We experience a story because we cannot perceive the whole shape at once. Our perception traces a path through structure. That path feels like time. Imagine standing inside a vast sculpture so large you can only see one part at a time. As you move, your view changes. The sculpture itself does not change, your position within it does. From the inside, it feels like progression. From outside, it is static. Time may be this kind of internal movement. This explains why time behaves differently under different conditions. Change the geometry, add gravity, increase speed, alter information flow, and the experience of time changes. Not because time is bending independently, but because your path through structure is changing. In this view, the universe is not unfolding, it is structured, and time is how limited observers move through that structure, why the future feels open. Even after accepting a timeless universe, one feeling remains stubbornly intact. The future feels open, undecided, full of possibility. If all moments already exist, why does tomorrow still feel uncertain? The answer lies in information, not metaphysics. From inside the universe, systems do not have access to the entire structure. They only have access to local information. Memory stores records of past states, but there are no equivalent records of future states. This asymmetry is not philosophical, it is physical. Information about the future is dispersed, incomplete, and constrained by entropy. To know the future in detail would require access to microscopic configurations far beyond what any physical system can hold. Uncertainty, then, is not a flaw in reality. It is a limit on access. This is why the future feels open, even if in a block universe sense it already exists. Existence does not imply accessibility. A locked room exists even if you cannot see inside it. Choice operates within this limitation. You act based on incomplete information. Your decisions alter local configurations, which affect what information becomes available next. From inside the system, this feels like shaping the future. From the outside, it is part of the structure. Both perspectives are valid. This preserves meaning without requiring fundamental indeterminacy. What matters is not whether the future is metaphysically open, but whether it is informationally open. And for beings like us, it always is. Time beyond humans. It is tempting to think of time as a human experience, something tied to memory, language, and planning. But time-like behavior appears wherever systems process information asymmetrically. Animals experience time differently than humans. Insects perceive rapid change. Large mammals experience slower subjective pacing. Even plants respond to temporal patterns through growth cycles and chemical signaling. Time emerges wherever systems respond differently to earlier and later states. This suggests that time is not exclusive to human consciousness. It is a feature of complexity. At the same time, different systems may experience time very differently. A star evolves over billions of years. A particle interaction lasts fractions of a second. A geological process unfolds over epochs. None of these systems require a universal clock. Each system has its own internal rhythms, defined by energy flow and structural change. Time is local to each system. This reinforces the idea that time is not a single river flowing through the universe. It is a collection of currents, each shaped by context. If there are other forms of life elsewhere in the universe, their experience of time may be radically different. Their biology, environment, and information processing could create temporal experiences unlike ours. Time may be one of the most flexible aspects of reality, not because it is unreal, but because it is adaptive. The quiet resolution, after everything that physics, philosophy, and experience reveal, the question is time real, finally loses its urgency. Reality does not need time to exist. This experience does. Time is real where it matters, where systems remember, anticipate, and respond. It fades where those conditions disappear. This does not make time fragile, it makes it contextual. The universe may be timeless at its foundation, but it is generous enough to allow time to emerge. And within that emergence, everything meaningful occurs. This realization does not demand awe or fear, it invites calm. Nothing essential is being carried away, nothing important is slipping past you. The structure that allows this moment also allows every other moment. You are not late, you are not behind, you are exactly where perspective happens. And in a universe that may not rely on time to exist, that perspective is not temporary in the way we fear. It is one expression among many, complete in itself. If there is rest to be found in science, it is here, not in stopping time, but in understanding that reality is larger than it. Resting in a timeless idea. If time is not fundamental, then the universe is not rushing anywhere. It is not counting down, it is not leaving moments behind. It simply exists, and within it, patterns arise that can remember, anticipate, and reflect. Those patterns experience sequence. They call it time. You are one of those patterns. The moment you are in is not being pulled away from you. It is one place among many in a larger structure, experienced from the inside gently and locally. Nothing needs to hurry in that sense. The idea that time might not be real is not unsettling. It is calming. It suggests that reality is not slipping through your fingers. It is already complete. You are not late. You are not early. You are simply here. And in a universe that may be timeless at its deepest level, that is a perfectly natural place to rest. A place to rest. If time is not fundamental, then nothing is rushing you forward. Nothing is chasing you from behind. Nothing essential is slipping away. The universe may be complete in a way that does not require motion. And within that completeness, moments arise that can be experienced, remembered, and felt. You are inside one of those moments now, not because time is pushing you into it, but because this is where perspective happens to be. There is nowhere else you need to go. In a universe that may be timeless at its deepest level, urgency is optional, meaning is local. And calm is not something you have to create, it is something you can allow. If this quiet journey through time and reality has helped you slow down, focus, or rest, you're always welcome to stay with the channel for more calm explorations of space, science, and the deep structure beneath everyday experience. For now, there is nothing to solve, just this moment.